And that is all I have for announcements tonight. Without further ado, I'm very happy to welcome Garry Felker. He's a local flight instructor based down at Sunrise Aviation at Orange County Airport. That happens to be where I got my private license 42 years ago. Egads, it's been a long time. But as I say, he did a great job on SkewTs last week, and I think you'll enjoy the talk. So Garry, take it away.
All righty. Well, welcome everybody. Normally, I do this with a whole bunch of weather review, but Mike asked me to kind of stick to just the SkewT diagram. So in order to do that, I still have to touch on some weather. So you have to bear with me, or the diagram doesn't make any sense to you. So I'm going to go ahead and share my screen here. And all right, hopefully that's working for everybody. So we're going to start off with the things that we typically concern ourselves with when so we have probably some VFR and some IFR pilots here, and so we're concerned about the visibility and the ride and whether we've got clouds and moisture and all that. And then if we're pilots that are flying IFR, we're concerned about icing and embedded thunderstorms. So those are our biggies for us. And all of this involves temperature, pressure, and humidity. So when we're doing calculations for density altitude in general aviation, we typically only concern ourselves with temperature and pressure. We don't really factor humidity in there, but in fact, this is very important when it comes to talking about weather, because water vapor is lighter than air molecules, the water vapor molecules. So even though water seems like it's pretty heavy compared to air, in fact, when we add vapor to the air, it makes the air less dense. So this is something that's important to keep in mind as we move forward here. In terms of the moisture, one of the things that's really important about it is that it moves heat around. And by that, what I mean is that at the equator, when we have direct sun hitting the earth, it gets really, really warm, and we have a lot of evaporation going on. And then at the poles, where it would normally be incredibly cold, we have a lot of condensation going on. So why does that matter? So it matters because for example, if you climb out of a swimming pool and there's a breeze and the water's evaporating off your skin, it cools you down because the process of evaporation takes energy, takes heat, and so it removes heat from the environment when we have evaporation occur. It takes that in. And conversely, when we have condensation, and we know when we have condensation because that's something that we call visible moisture, right? So be clouds or fog. When we have condensation, heat is released. This is very important going forward. So you got to keep those two facts in mind as we move forward and talk about what's going on with our weather. The other point, which you're probably all familiar with, is that if I have a parcel of air and it's a given temperature, if I cool that down, assuming that there's some humidity in that air, at some point it will get so cold that it can't hold the moisture anymore, and we'll get visible moisture. So this is really what happens when clouds form, is that the temperature of the air got cold enough that it couldn't hold its moisture anymore. It reached its dew point, and we had visible moisture. So when we listen to the ATIS, we get the temperature dew point. The whole purpose of that is to keep in mind whether or not we've got a 3 degree or less spread, which means, hey, we're getting really close to the dew point. And if we get close to it, the air gets cold enough that we have visible moisture and clouds. So that's one of the considerations that we have. Okay, this chart I'm going to spend a little bit of time on because it's also a prelude to the SkewT diagram, and it's something that's, you just got to understand this in order to make sense out of the SkewT diagram. So I'm going to talk about 3 different lapse rates. The first lapse rate is our environmental lapse rate. That's the actual temperature change and humidity and winds and such in the atmosphere. We get that data with weather balloons. There's some 90 sites in the United States where they send up weather balloons. And we do this every 12 hours, pretty much on the dot every 12 hours. So at any given point in time, we could be working with data, and this is all weather forecasters, that's up to 12 hours old. So that's one thing that we need to keep in mind when we're trying to predict what's going to happen with the weather. So the lapse rate that the weather balloons get as they ascend into the air are supposed to be over a given point, but it doesn't always work that way, because they catch winds and stuff, and by the time they get done ascending, they could actually be 250 miles away from where they were let go. So we have that to deal with as well. But it does collect data. It radios it back down to a receiver on the ground, and then that data is collected by the Weather Service, and they process all of this information in order to give us forecasts. These little packages that are sent up with the balloon are probably about $300 worth of value, and they carry with them a mailing envelope that's free postage for people to return it if that happens to show up in their yard or something. So that's something that just you might want to be aware of. Okay, so that's the actual lapse rate that happens in our environment. Oh, and by the way, we typically refer to this as 2 degrees C per 1,000 feet in terms of cooling, which is completely an average. It's not at all representative of reality at any given point. In fact, if we had an inversion where the temperature is actually warming with altitude, that would clearly contradict this loss of 2 degrees C per 1,000 feet. So, but that's where that 2 degrees C came from, is the average change in temperature that these weather balloons collect. Okay, so now I got to go into two other lapse rates, and it's the dry and moist adiabatic lapse rate. So let's first define what adiabatic means. So adiabatic means that the actual word breaks down into not passable. And what that means for us is that we have a temperature change with pressure, but we don't remove heat or add heat to the parcel. So this involves lifted air. So if I lift a parcel of air from the surface and I neither add nor take away heat from it, as it rises, as I lift it in the atmosphere, it becomes under less pressure because we have less pressure as we climb up in the atmosphere. And when we do that, it will cool simply because it's under a lower pressure. And if I were to take that same parcel of air and bring it back down to the surface, it would regain all of its heat as we pressurized it as we came back down. So how do we break this in? We break this into two pieces, dry and moist adiabatic lapse rate. So dry is a little bit misleading because it could be up to 99% humidity. All it means is it's not saturated. The minute we get saturated air, then it becomes a moist adiabatic lapse rate. So why do I care? The dry adiabatic lapse rate, this unsaturated air, if I lift a parcel and it simply changes temperature because of the pressure change, it's going to change uniformly at 3 degrees C per 1,000 feet. So it's very predictable. It's very straightforward. We can pretty much count on that dry adiabatic lapse rate to do that. The minute we have condensation, the minute that we reach saturation or 100% humidity, now we're talking about the moist adiabatic lapse rate, and it won't cool as quickly as the dry adiabatic lapse rate. So why is that? Well, the reason is that, remember, we just said a minute ago, when we have condensation, there's a release of heat. So if I take a parcel of air and I lift it and it has condensation, in other words, it reaches its dew point as it cools, the minute that happens, as I continue to rise to lift it into the air, the minute that happens, it's still cooling, but it's cooling at a slower rate because when there's condensation, it's generating heat. So it's going to cool between 1.1 and 2.8 degrees C. It won't cool as fast as the dry adiabatic lapse rate. This condensation process is slowing down the cooling process. So this becomes very important going forward as well. So what can lift the air? So there's a variety of things that can lift the air. It can be lifted by a front. I'll talk more about that in a minute. It could be a dry line, a low pressure area, could be terrain. Some folks have asked me they say, I remember dry line. I don't remember what that is. So a dry line is typically, you typically find that kind of to the west of Texas, and you have the Gulf air, which is really moist on one side, and you have dry air from the west on the other side, and that's called a dry line. And both air masses are typically the same temperature. So how could that cause lifting? Well, again, because the moist side from the Gulf has humidity in it, we know that humidity lowers the density of air. So when these two air masses come together, the dry air pushes up the less dense moist air. So that's why a dry line can provide lifting. So all of this sounds a little bit redundant, but bear with me. It plays into the SkewT diagram here as we get further on. Okay, here's just an example of a low pressure area. We have the sun, it'll heat the Earth's surface. When it does that, it heats up the air and that air expands. As it expands, the cooler air, more dense air that's around that area pushes that air up, and that creates a low pressure area. So, and then as that column expands, it falls back over into the cooler, more dense air area. And then we wind up with weather patterns and circulations based on the high and low temperature areas. But the thing to keep in mind about this is that when you have a high pressure area and a low pressure area, the low pressure area is air that's being lifted by more dense air around it. So this is an example of a lifting process because of a low pressure area. Fronts are also all lifting mechanisms, right? So a cold front is cold, dense air moving towards comparatively warmer air, and it moves pretty quickly. Cold fronts move between 20 and 25 miles an hour, and it has a fairly steep gradient. So its lifting is fairly significant compared to a warm front, for example. So there's your lifting with the cold front. The warm front is less dense air, and it's moving in on cooler air, which is more dense, so it tends to climb up over the top of it. A lot of times it's associated with local rain, whereas the cold front can sometimes be associated with convective activity, but also still climbing, so there's a lifting involved, right, because it's climbing up over cooler air. And we've got stationary front, same kind of deal. Cold front and warm front kind of park up against each other and don't move. We have air that sits there and sometimes can produce rain for days. And the reason, of course, is that we've got this warm air in it that has enough humidity in it. When it gets lifted, we get condensation and we get clouds and potential rain. And then the occluded front, which is really kind of interesting, is like a warm front trapped in between two colder air masses. So the warm front's moving forward and gaining on cooler air. It's climbing up over it. And just as it's getting involved in doing that, a cold front comes along behind and lifts both of them. So we have both cold and warm occluded fronts, and they're very similar to each other, but the common theme there is that the warm front has got a lot of lifting going on because it was climbing to begin with, and then it gets shoved up even higher. So a lot of times these occluded fronts can kick off some pretty significant thunderstorms, but every one of them involve lifting. So this is something that I want to point out. Here's an example. Everybody's seen prognostic charts. And what I'm going to do is I'm showing, this is a look into the future. This is a 12-hour one. And you can see that we've got cold fronts on here. There's an occluded front right here. It's kind of hard to see. And then we've got some troughs and a warm front over here. So we've got all the players here on this chart. And what I'm going to do is I'm going to step you through. This is 12, and then I'm going to go 24, 36, and 48 hours. And what I want you to see, if you're looking into the future here, is where these fronts are going and where they're moving. So kind of get a mental image of what this looks like. And I'm just going to go ahead and click on it here. And we're going to move forward 24 hours. See, it moved a little bit. The cold front off Florida moved out, and the cold front here in Southern California moved in a little bit. Here comes 36 hours. Everything tends to move eastward. All these fronts are attached to a low pressure area. So low pressure areas are counterclockwise because of the Coriolis effect, and high pressure areas are clockwise. So these fronts tend to move counterclockwise around a low. And then here's 48 hours. So we see all of our weather patterns tend to move east, and they're attached to a low pressure area. And here I was able to go click, 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 and see what was happening over the next couple of days in terms of fronts, which provide lifting mechanisms. So that's a good example of that. Here's an example of what we call orthographic lifting. This is terrain causing a similar type of a function here. We have adiabatic cooling on one side of the mountain and then adiabatic heating on the other side. So this is typical of our Santa Ana winds. That's kind of unique here to our coast. You know, we get a big high pressure area out over Utah sometimes, and it's going clockwise and it's pushing air towards our local mountains here up over, you know, just north of us. And as it comes near the mountain, it gets forced up. It has nowhere else to go. And so what we wind up with is clouds and sometimes potential rain, and then moisture leaves this air because of the rain, and the air comes up over the top of the mountain and then swoops down the other side of it. And of course, now it's being compressed, it's being pressurized as it comes down the other side. So it's heating, it's warming at 3 degrees C per 1,000 feet because it's now dry descending air, and that's where we get our dry Santa Ana winds. So this is simply another example of a lifting mechanism. So we've discussed a few of them now: low pressure areas, fronts, dry lines, and terrain. All right, so this diagram is, I'm gonna kind of make this all come together here shortly. This diagram is showing a relationship between temperature and altitude. And I'm showing the dry adiabatic lapse rate, which is 3 degrees C per 1,000 feet, right? So this is very consistent, and this is a lifted parcel. This is if we have lifting. So we've talked about all the ways we can lift air. If we lift a parcel at the surface and it's not saturated, then it's going to follow this line. It's going to cool at 3 degrees C per 1,000 feet. Then we've got this moist adiabatic lapse rate, and notice that it's cooling at a less severe rate, right? It's cooling something less than 3 degrees C, right? So it tends to stay warmer than the dry adiabatic lapse rate. And again, that's because we have condensation going on with the moist adiabatic lapse rate, which is a release of heat. And when that occurs, it cools, but it doesn't cool as fast as the dry adiabatic lapse rate. Okay, so these were both examples of lifted parcels. Now what I'm going to do is I'm going to add an environmental lapse rate. Now this would be the lapse rate that a weather balloon would pick up, right? And I'm just going to throw it on here, and then I'm going to talk about it. So here's an example of an environmental lapse rate that just so happens on this given day is cooling as it rises up, right? It's cooling, but it's not cooling as fast as either the moist or the dry adiabatic lapse rate. In other words, moist and dry adiabatic, so a lifted parcel is going to be cooler and more dense than our actual environment. And we call this very stable air. This is, there's no chance for a thunderstorm to develop in a situation like this. So in terms of lifting, it would be like picking up a rock off the bottom of a swimming pool and letting go of it. It's just going to sink right back down again. There's no convective development, no lifting mechanism that's going to work here. But if the actual environmental lapse rate happened to be cooling at a greater rate than the moist or the dry adiabatic lapse rate, it would look something like this. And in that case, this would just be our standard, you know, whatever's going on in our atmosphere that day, this line right here, the green one. And if I took a parcel of air and lifted it, it's when, regardless of whether in this case it was moist or dry, if I lifted it, it's going to cool more slowly than the actual environment. And what that means is it stays warmer than the environment and less dense. And then it's off to the races. And this is ripe for convective activity. So this is considered a very unstable atmosphere, right? Again, I need lifting for this to occur. And we're going to talk a little bit more about that shortly. But this is what it would look like if we were talking about an unstable rate. And then I could take this green line. I had it over here before, and then I moved it clear over here, and it could be anywhere in between, right? So this is varying degrees of instability, depending on where this line falls. All right. So for thunderstorms, for example, and this is something that affects all of us. If we're IFR, we're worried about it because it could be embedded and we might not see it coming. If we're VFR, we can see it. And in all cases, we want to stay clear of that, right? So it takes three things in order for a thunderstorm to occur. I need an unstable atmosphere, and I just told you how that could occur. I need a lifting action. Something's got to be in play lifting air parcels at the surface. And there's got to be enough moisture in the air to begin with for this to all happen. So all three of these things are important, and we're going to talk a little bit about how I can look at that. One of the things that I need to talk about, this is an example of an inversion layer. We have these off the coast, creates our stratus clouds all the time. And what we have is the marine layer that sits out over the ocean. The water out off of our shore, off of our coastline, comes from Alaska. So it's unusually cold water compared to the land, because we're a desert here in Southern California. So we have a nice contrast there. And out over the ocean, we get mixing because of wind and stuff. And so we get a lot of moist air. And as it rises, it cools, and then we get stratus clouds that form. But then we get an inversion layer because we're under something called a Pacific high. We're at the horse latitudes. This all gets into the Coriolis effect and why we're under a constant high pressure area most of the year. And that's a different weather presentation I have, but just trust me that what we have typically a lot is this thing called an inversion. And that means that it was getting colder, then it gets warmer for a while, and then it gets colder again. So this red line is representative of our temperature. And when this occurs, we can wind up with all kinds of issues in terms of winds. We can have wind blowing one direction underneath the inversion and wind blowing another direction on top of the inversion. And so this is something that creates issues for us in terms of turbulence. So we're going to look at an example of how inversions create turbulence on the SkewT diagram. It's one of the things we can pick off of the diagram. And this is an example of how that occurs. And it's also the whole reason, if we're shooting an approach, that our approaches aren't perfect, because all of us obviously would shoot perfect approaches if it weren't for the fact that we had inversions around here and a little bit of instability, right? So it's, at least that's my excuse. All right, so here's another example of where we have an inversion and we have wind shift. There are other things that can cause wind shear. These can be winds that are blowing around buildings or terrain as we're shooting an approach. It can be downdrafts from convective activity. We can have a front moving through. Anytime a front moves through, we know that we're guaranteed a temperature change, a pressure change, and a wind shift, guaranteed if a front comes through. So that potentially can cause some of these wind shear moments. And obviously, if you're following an airliner in on an approach, you can get caught up in some of their wake turbulence if you don't stay a little bit higher. So these are all things that we're concerned about. We'd like to know if there are wind shifts as we transition through the atmosphere. Fog, I'm not going to spend a ton of time talking about this. There's all these different kinds of fog over here, but the one thing they all have in common, this is something that we're going to keep harping on here, is that the moist air that contained all of this moisture got so cold that we had condensation, and that creates clouds or fog. So it's air that got too cold to hold its moisture, and there's the result. Okay, so we're just about to get into the SkewT diagram. The things that we've just talked about are inversions. I didn't talk about the freezing level yet, but we'll get into that. Temperature dew point, when we get those two numbers coming close together within 3 degrees C or so, we get condensation. That's clouds, that's moisture. Wind shear, we talked about that. Thunderstorm potential, and then clouds, tops. So I have a whole thing on clouds, but in this case, what we're really interested in is where are the tops and where are the bottoms. So usually the bottoms are reported, but the tops are not unless you get a pilot report or you go to windy.com or one of these other websites that tries to give you that information. But I'm going to show you how to get that off a SkewT diagram. Okay, so here's what it's going to play into. We're going to wind up with a surface diagram, surface depiction, or we're going to wind up with a prognostic chart because we want to look out a little bit, a few hours or a day or two, and the Skew-T diagram. With these two together, I can get almost all the weather that I want to get. It works out pretty well. And as we're going through this, I'm going to move pretty quickly, but I'm going to give you some useful points to take with you. And then if you want to follow up and study it on your own a little bit later, that'll be on you if you're interested in doing that. Okay, so here's a picture of a Skew-T diagram. Some of you have seen it before, some of you haven't. It looks pretty busy. There's a lot of lines on it. I'm going to break them all down for you. But before I start, I'm going to tell you what some of the disadvantages of a Skew-T Log-P diagram are. There are multiple sources for these things. Different organizations that put them out. A lot of universities put them out. I have an app on my phone I'll show you here in a bit, and some websites that you can go to get these things, and nobody uses the same colors. So you can't get hung up on the colors on a Skew-T diagram. You just have to be prepared to interpret it based on what the lines look like. You can't go, well, okay, as long as I know where the green line is, I know what this is going. You can't do that. They're never the same depending on where they come from. We mentioned this earlier, we only get data twice a day. That's every 12 hours. So there's a little bit of a disadvantage there because we're guessing, right? We're analyzing and guessing what might happen based on the data that we have. And the Skew-T diagram is no different than that. I also mentioned that the sounding doesn't give us a true vertical thing because the wind can, a vertical spot to say, okay, we know that over this area this happened because the balloons shift because of winds. And the other thing that happens is that it takes several minutes to travel from the ground up through the top of the atmosphere where it gets done collecting data. And so we don't have an instantaneous view of it. And there are other things that can confuse the weather balloons. For example, if they're going up, it could be a really dry day, not a lot of moisture in the air, and it goes through a cloud. And it goes, oh, well, there's a ton of moisture in the air. And then it reports that, but really it's just because it happened to go through some standalone cloud. And so there are difficulties with the data that we collect. We have to work around them. Everybody does. But it's the best thing that we have. And it's what we use to try and figure out what's going on. Okay, so this is the Skew-T Log-P diagram with no data on it. This is just the background plain chart, and there's still a bunch of lines on it, and I'm going to talk about what those lines mean. One of the things that I'll point out right away is that on the left side of the chart is millibars, which is our atmospheric pressure, and some of the Skew-T diagrams, this one included, give us feet on the right side. Some of them do, some of them don't. You can, if you're unsure how to convert millibars to feet, you can Google that. There's all kinds of calculators online that'll do that for you if you happen to be using one of these charts that doesn't give you feet on the side, because that's what we work with most of the time. All right, so, and then by the way, you notice here that the chart has about 1,000 millibars at the bottom, and we know that our 29.92 inches of mercury is the standard average, what we consider a normal day barometric pressure at mean sea level, and that equates to 1,013 millibars. So sea level is right here at the bottom of the chart. Chart even goes slightly below that. All right, so let's break it down. Here's the first set of lines. These are temperature lines. So basically they're from here's minus 50 degrees C up to plus 50 degrees C on this chart. And these, normally you would expect that along the bottom of the chart, wherever you had a temperature designation, it would go, the line would go straight up. But they've taken these lines and moved them to a 45-degree angle to the right. And the reason for that is that when we collect data from the weather balloons and we're going to put it on these charts, we want the data to kind of go pretty much up vertically on the chart and not run off the left side of our chart. So what they've done is they've skewed the temperature lines to the right, and that's where the Skew-T name came from when we talk about a Skew-T Log-P diagram. So it's Skew-T because they've skewed the temperature lines 45 degrees to the right. And that way, most of our environmental data that we collect pretty much goes up vertically on this chart and doesn't run off the left side of it. So these are the temperature lines. Very uniform, very predictable, no problem identifying those. These are the pressure lines. And the pressure does not change uniformly with altitude. It's not a linear change. And because of that, they plot the pressure or our altitude logarithmically. So for those of you that are math inclined, you know exactly what that means. For the rest of us, just trust it. It makes it so that we can look at the data visually and make sense out of it without having to worry about the fact that our pressure doesn't change uniformly with altitude. The other thing that I'll bring up along those lines is that typically for those of you that are instructors, for years I've been telling students that, we lose 1 inch of mercury per 1,000 feet in terms of pressure change. And effectively, I'm flat out lying to them because that really only works for the first 10,000 feet, right? So you can see here that if I go up to 5,000 feet, I lose 5 inches of mercury. Hey, that worked. That was great. Go up to 10,000 feet and I lose, well, not quite 5, but I could still make that work, right? But after that, forget it. It just all falls apart to the point where between, for example, 45 and 50,000, I only lose 1 inch of mercury, right? So just another point in play here as to why we plot this data logarithmically. Okay, these are the dry adiabat lines. Now remember, we like these lines because they're very consistent and they're very predictable. And this is unsaturated air. This is air that is, remember, we're talking about adiabats. This is going to be lifted air parcels, right? So this is why we care about the dry or the moist adiabatic lines. It's lifted air. And when it's dry and it's not saturated, there's no condensation, there's no heat being generated. It's going to cool at a nice 3 degrees C per 1,000 feet. So this works out great for us. Nice and predictable, looks really uniform, plays nicely with our data. This is all great. And now we're going to get to the moist adiabat line. What these temperatures do with the moist air, which is making condensation and releasing heat, is kind of all over the place. This reminds me of a cat climbing out of a bathtub. It's like it's a mess, right? So when the air parcel is really, really cold, this line right here, I hope you can see my mouse here, it actually tends to follow, I'm going to go back one here, the dry adiabat lines, because it's so cold, it doesn't hold very much moisture to begin with. But as we get warmer and the air can hold more moisture, if I lift it, and these are the moist adiabat lines, if I lift a parcel that's reached its saturation point, it's saturated air, this is the path it's going to follow, and it's all cooling. Like this line here over to the right, it looks like it's like it might even be getting warmer. But remember, the temperature lines are skewed 45 degrees to the right, so this is actually cooling. It's just not cooling very fast because there's going to be condensation and there's going to be heat release. So this all, bear with me, this all comes together here real quick. So that's that. This is the mixing ratio. This is what tells us what happens to the humidity in our air. So if I have humidity, it's going to change with temperature, and we use these lines for that. So this is the mass of water vapor compared to the mass of dry air, and I'll show you how to use that here in a minute. We're going to break that down. So that's all 5 of the background lines in this chart. So here's another example of the chart. In this case, here's what we're looking at, right? So this is where we can start to make sense out of things. The red line on this particular chart, and it's not always red, depends on where it comes from. This red line is the actual environmental temperature up through, I don't know, 45,000 feet, something like that. And the blue line is the humidity level. So if I look at this chart, and I can see here that this distance between these SkewT lines, these temperature lines that are going off at a 45 degree, this is about 10 degrees difference here, right? So the closest, the humidity line, the humidity and the temperature line come together is about 10 degrees. So I can look at this and I can go, you know what? In this entire area here, there's no clouds. There's not going to be any clouds because the temperature and humidity, the temperature and the dew point are farther apart than 3 degrees C, except right here at the surface. Right here at the surface, they're touching. And this was January 9th, I pulled this. And I don't know if any of you fly out of John Wayne or Long Beach, but I pulled the METAR for Long Beach, and it said that we had a broken ceiling at 400 feet and we had mist. And at John Wayne, it was reporting fog and about the same. So that's because right here at the surface, the temperature and dew point came together. We had visible moisture. And what I also can tell from this chart is that if I took off out of one of those airports, which I could do, right? We could take off in 00 if we really wanted to. Not very smart, but we could do that. Where they're touching, we had all of this moisture, mist and fog, and it wouldn't take long. I mean, really quick, as I climbed up, as I took off, I'd be in the open. It would be clear and beautiful, sunny day, and I wouldn't have any moisture at all because the dew point is going so far to the left here as the temperature goes up. And by the way, here's the temperature line, right? I can tell right now that I have an inversion right here, and an inversion traps air that wants to rise. So that's an important thing to remember about inversions. So it gets up to what looks like, here's 1,000 feet, here's 5,000 feet. Looks like about 2,000 feet, it's warming as I climb, and then it starts cooling again as far as the temperature goes. So what else can I pull off this chart? Just this first chart. How about freezing level? So here's the 0 degree temperature line. If I move up this temperature line here, boom, I hit this is my environmental line, hits the freezing point. If I move clear over here, it looks like about 12,000 feet. So I know that my freezing level is 12,000 feet. Now, can I fly here today if I'm up flying around? Yeah, there's no clouds. There's no chance of clouds at the freezing level. It this looks like not such a bad day to fly. And the other thing I can pull off this chart, all this stuff on the very first chart, and there's other stuff we can look at here too, but I'm just going to tear this chart apart right now. What we have over here is this blue line represents the speed of the winds up through the atmosphere. So this is great, right? Because we're used to thinking of winds at the flight level we're flying at, right? We're interested in those winds, and it helps us with our flight planning. But what if we had to change altitude for some reason? Wouldn't it be nice to know what they're doing as we go up? And in this case, it looks like a relatively steady increase in winds up through about, I don't know, 35,000 feet. And then there's a little bit of variation here. And this chart goes up to 100 knots, right, in terms of wind speed. And then these are your traditional wind barbs, right? This just shows you the direction the wind is coming from. These wind barbs right here are saying that the wind is coming from the northwest. And the flag on here, as you're well aware of, is 50 knots. The long barb is 10 knots and the short barb is 5 knots. So we can see that the winds are fairly consistent here. They're, for the most part, out of the northwest, a little bit out of the west down here at the surface, and they don't change much. So I'm not looking at a lot of turbulence or a lot of shearing, wind shear. I'm not looking at hardly any of that on this chart. So this is a relatively nice day. This plot over here is representative of the winds, and I'll show you that a little bit later when I get to one of the live charts. And we're going to talk about some of the other things we can pull off these charts. Here's an example where I've zoomed in on a chart. So basically, this is 1,000 feet, 5,000 feet. I'm just at the very bottom part of one of these charts. And we got winds here coming from the southeast, and then wham, they flip around and they're coming from the northwest. And then over here, now they're coming from the east. And then up here, they're coming from the north. And so we've got, this is like within our flight range, we're flying smaller aircraft typically from the surface up to, in the vicinity of 10,000 feet, a lot of wind change going on. So this is implying to me that we're going to have a bit of a bumpy ride. Now, in terms of temperature dew point, nice separation here. I don't expect to see any clouds. So that's good to know. This was near Santa Ana on this day, whatever it was, February 15th. So not too bad of a chart, except that it's going to be bumpy flying around here. Now this chart is a lot of fun. So I got to spend a little bit of time here with you on this chart. This is great. So what we have here is this red line. The red line, you can't see it because I've got this dashed yellow line on top of it, but it starts down here at the bottom. It goes up here towards the left. It climbs here. You can see it just to the right of this blue area. And then it climbs up all the way up here, right? So, and then heads off to the right here. So this red line, just the line itself, is the environmental temperature of our environment, right? So they sent up a weather balloon and this is what it did. This is the humidity line, right? So this is our dew point line right here. And we can see that right in this area, they're starting to get a little bit close, but still, I don't think I would expect to see visible moisture here. And they stay fairly separated. So that's great. So what's the problem? What's all this area that I colored in pink here? Well, let's talk about it. So this is where we get into how to use this chart. So what's happened here is that if I took a parcel of air and I lifted it, right? If this is the temperature it is right here at the surface. Let's look to me to be about, let's see, maybe 32, 33 degrees C, something like that. If I took this and I lifted it, it would cool. Remember these swooping lines that are all very uniform, that are the dry adiabat lines? So it would cool if I lifted it at 3 degrees C per 1,000 feet, right? Until we had condensation. And I'm going to tell you how I would know that this is the point I would get condensation. So this is the LCL, that's the lifted condensation level, right? It's a lifting condensation level. And the minute I get condensation, now it switches, and instead of cooling at 3 degrees C per 1,000 feet, which is the dry adiabat line, now see these darker gray lines are the moist adiabat line. Now it's going to track the moist adiabat lines on up. So there was a change. The minute we had condensation, there was change. Now, if I lifted the air parcel from here up and I only lifted it as high as the LCL, the lifting condensation level, it's colder right here than the environmental air, which means that it's more dense. And if I only lifted it this high and I let go of it, it would sink right back down again. But if I could lift it here, where because it was cooling at the moist adiabat rate, I got up past this LFC, which is the level of free convection. If I get it past that point, now it's cooling and it's staying warmer than the environmental rate. And so now it's like a cork. It's like letting a cork go in the water, and it just wants to go. It just wants to keep going. And this is ripe for right here. If I can lift past the level of free convection, then we're off to the races if there's enough moisture in the air to get thunderstorm activity. This is ripe for convection. So this is one of the beautiful things about this chart, is that right away I can see, because a lot of times you can get some of these places that create these charts will draw this line for you, or you can create it yourself if you know how to read the background of the chart. And this will stay unstable. This pink area, all this pink area is unstable all the way up until the equilibrium level, where all of a sudden now it's cooling. It's still following the moist adiabat line, but it's cooling. And it gets to the point where it's now colder than our environment, and so we don't have any more lifting. This would be where the thunderstorm would top out. The thunderstorm wouldn't want to go any higher than this, because this is literally like a little inversion that's stopping the thunderstorm from developing. So this area here, this cape, is called the convective available potential energy. And that number typically on a normal day around here in Southern California is less than 100. I've seen it as high as 6,000 something. And anything over 1,000, anything like 1,000, 1,500, 2,000 gets to the point where we're really unstable, right? So this is good to know when we're looking at whether or not we're going to have unstable air. Now here's an example of an airport. This ECP airport is in Florida, and it's on the northwest side of Florida. It's right over here. And so what do I have here? This purple line is the lifted air mass, right? So it followed it's a little bit harder to see here, but it followed the dry adiabat cooling and then flipped and switched to the moist adiabat cooling and came up like this. And we can see that we have some what we call CAPE right here. And this CAPE is listed as 1,620. So a fairly significant number for CAPE, right? And we have a lifted index of -3. That's always with reference to the 500 millibar line, which is right here. And so it's basically saying that there's a -3 degrees change here. So that's also indicating some instability. The winds are fairly calm, or fairly consistent. That's nice. It's not too turbulent, but we have the potential for convective activity here because the lifted line is off to the right. And this was, when did I do? January 26th in Florida. And then I look at my prog chart or surface analysis chart, and I look, and here is a cold front blasting right through where this airport was. And I can see that there's moisture here. So what do I have? Unstable air, a lifting mechanism, and moisture. Those are the three things I need for thunderstorms. And guess what? Here they are. That's where all the thunderstorm strikes were, just right where this all happened. So I pulled all of this data at the same time. And just by knowing whether or not I had a lifting action and moisture and looking at this SkewT chart, I could immediately tell that we're likely to have thunderstorm. So that's an area I probably wouldn't want to fly in, right? So that's kind of a cool use of that chart. Now I'm going to explain a little bit more about if, for example, this purple line, which is the lifted parcel line, right? Here it is cooling at, here's this blue line here is the dry adiabat line. Here it is cooling at the dry adiabat rate. And then it flips. This is the lifted condensation level. It flips and cools at the moist adiabat line. How do I know where this spot is? Well, remember these angled lines that we talked about? The temperature lines are here, right? They're angled. But this lifted index, these lifted index lines are what the dew point would do if we lifted an air parcel. So here's what we do. We take where the dew point line is and we track it against these gray lines. So we're going to follow that up parallel to the gray line, right? Until it hits wherever the environmental, this would be the moist, in this case, the dry adiabat line would be. So here's where the temperature starts at the surface. It follows the dry adiabat cooling up till here, and where that meets the dew point line following this index line here, that's where the lifted condensation level is. So if I lift it, so even though the dew point and the temperature are far apart, and I wouldn't normally have any visible moisture, if I lifted a parcel at this point here, which looks to be about 7,000 feet, right? Here's 5,000 feet, about 7,000 feet. If I had lifting going on, I would at the very least have visible moisture. I would have clouds, right? I wouldn't have, there's no chance of convective activity here because that lifted parcel is going to stay colder than the dew point and the dry and the environmental temperature. So there's no chance of convective activity here in this drawing, but I would get clouds if I had a lifted parcel. So this is the dry adiabat line that we followed from our surface temperature. This is the mixing ratio line that we followed for the dew point, and where they cross is my lifted condensation level. right? And then at that point is where I'd start following the moist adiabat line on up. So that's how you would, if you had a chart and you didn't have this line, they didn't provide it for you, you could create it yourself. Okay, here's another, this is an app I have on my phone, Skew-T Log Pro. I like it a lot because I can really quickly access things. And let's see what this chart is showing us. So here's our temperature line, here's our dew point line, and I can see that they're right on top of each other all the way up through about 12,000 feet. So I've got visible moisture from the ground up, right? So that's one thing. And then on top of that, here's my 0 degree temperature line. So from about 5,000 feet to 12,000 feet, I'm at freezing temperatures. So guess what? We have visible moisture and freezing temperatures. There's icing, right? There's icing for you. So this is not a place I'd be wanting to fly right now. Now, if I look at the purple line, this is our lifted line. If we lifted a parcel of air, no chance of convective activity here, but look at the wind pattern here. So out of the northeast here, and then within a couple thousand feet, it's shifting and it comes out of the southwest. Like this is a 180. You know why? Because this is effectively right here, the way that this temperature is going. It's not really cooling very fast as we go up. So it's like an inversion right here, and then it does what it normally would do. So not only do we have visible moisture and icing, but I've got effectively a strong wind shear going on here at 5,000 feet. I would not be wanting to fly in this. This would be something, I would look at this chart and in a heartbeat, I'm not going there, right? This is like not something that would be any fun for anybody. So, and then once you get up higher, you can see that the temperature dew point are far apart. If you could get up to, I don't know, 14, 15,000 feet, you could fly through here and you would have some winds, but they're strong, but they're from the same direction. They're not switching around. It's not bad. If you were flying eastward, this would be great. You'd have a nice tailwind. And I can tell that I wouldn't have any visible moisture because the temperature dew point are fairly spread apart up near, 14, 15,000 feet. So it's only down here in the lower areas that I just absolutely not going. And speaking of icing, when we're talking about pilot reports, typically, if we look at the frequency of icing on pilot reports versus the forecast temperature, we get most of our pilot reports for icing between -2 and -15 degrees C. So if you've got visible moisture and you think you're going to be flying at an altitude that's going to put you between -2 and -15 degrees C, that's not a good day for you. Let's not do that. One other interesting point here is that for years and years, I heard about these super cooled large droplets called SLD. And that's water droplets that are colder than freezing, but they're still liquid. And so when we're flying through this and it hits our plane, that's where ice comes from, right? Right away, boom, we've got ice collecting. But what's interesting about it is that they're literally defined as water droplets with a diameter of greater than 50 microns. So for those of us that are not machinists, you look that up, it's about 2/1000 of an inch, or about the thickness of your hair. And I'm like, that's a large water droplet, really? Like, I'm shocked that they call it that, but that's what it is. So for those of you that are familiar with this term, this SLD, it can be pretty tiny water droplets, right? It can be literally like what a cloud looks like. You can go, well, there's no rain out there. I don't see anything hitting my windscreen. There shouldn't be any ice building up, right? Wrong. It can build up. So this is why. All right, here's another source. This is a university, Plymouth State Weather Center. And you can Google this if you want. You can look it up. You go to upper air and then CONUS soundings, because all this data that these weather balloons collect are called soundings. That's what we call the data. And I tell it I want a SkewT diagram, and then I can pick various locations out here. These locations are where they let loose weather balloons. These are the 90 locations we talked about. And then computers can sit there and analyze the data from all of these locations. And anywhere in the country, they can tell us, they can generate a Skew-T Log-P diagram based on the data they collect from these balloons. So if I were to click in this case, I'm gonna go ahead and say, okay, I want weather down here in Florida. Why did I pick that? Because I looked at some weather forecasts and saw that there was the possibility of some thunderstorms. And this was, I pulled this yesterday, February 16th. And notice that there's a cape going on here. This is the yellow line. All these lines are different colors on these different charts. And it's pretty far out from this white line right here is the temperature. This other white line is the dew point line. The dew point is never on the right side of the temperature line. So if you're looking at these going, well, which line is which? The temperature is always going to be warmer than the dew point. They can come together, but the dew point can never be warmer than the temperature line. And I've got a CAPE value here of over 1,000. So pretty good potential here for unstable air. This is unstable air. Now the question is, and by the way, right down here, you can see how it decreased in temperature at the dry adiabat. That's where my lifted condensation level was. And then it flipped and started decreasing in temperature with the moist adiabat line because we had visible moisture from the lifting. All right, so, and this only gives us millibars on the left. I don't see that it gives us feet on the right, but you can convert that if you like. So we've got unstable air. And let me go back. In this case, if we look over here, here's the front that's coming through. I forgot to talk about this. This is a cold front. This is where all the lifting is coming through. And right here where we pulled this in Jacksonville, there's a truckload of lightning strikes. And we have thunderstorms, rain. We've got some icing going on here. We can see that here. So I have icing, turbulence, thunder, we have it all, right? And so we can look at this chart and go, yeah, well, I can see the potential for unstable air. All I got to do is find out, is there moisture and is there lifting? So here's the cold front, there's the lifting, here's the moisture. It's all in this area. We can see that depicted on here. And then we've got thunderstorms as a result. Okay, so these are some of the sources. 1-800-Weather Brief has a source. I don't particularly care for their Skew-T Log-P diagram, but it's there if you want to look at it. And lots of people get their weather from 1-800-weatherbrief.com. Skew-T Log Pro. And then what I want to do right now is I want to take you to this site. And I want to show you a little bit about this. So I got to stop sharing this particular screen and share a different one. So bear with me here.
And I copied if you can see the chat box, if you're online here and have a browser at the same time, I copied the link to the site he's about to go to, so you can go to it yourself and follow along.
All righty. So when you go to this site, it's from our government, the NOAA. It comes up with a whole lot of options. It looks a little bit confusing. And rather than me try to confuse everybody with all the variety of options you have, what I'll tell you is if you're going to play with this, go ahead and it'll default to the Op40. Go ahead and leave it there. Don't worry about any of the rest of these. And then we want to leave this box checked that says a latest. I want the latest analysis that they have. And then in this particular case, I'm going to look at saying I wanted to leave Fullerton and I want to go to Henderson. I want to go to Las Vegas. And Daggett is like about halfway in between roughly. So I threw that in there as well. And I want to look at the Skew-T diagram for these 3 spots. And I want 3 hours. I want current, out 1 hour and out another hour, because it's about a 2-hour flight, right? So I'm going to say I want 3 hours worth of data. I want Fullerton, Daggett, and Henderson. And then I want the interactive plot. So the latest 3 hours worth, I can go out way more than 3 hours worth if I want, but that's what I'm going to look at it for right now if I was going to leave tonight. And I'll go to the interactive plot. So here's what it brings up. Right now it's showing me Henderson. Let me go to Fullerton. This is the current Fullerton time, right? That's showing up. And then this is Daggett out 1 hour. So it would take me about an hour to get to Daggett. So this is what that would look like. And then this is Henderson. This is what Henderson would look like. And what you can see, if I just click through these, is that the temperatures, the temperature dew point spread doesn't look too much different at Fullerton. Everything gets a little colder as I go towards Vegas, right? Watch everything move to the left a little, move to the left a little, and then an hour later at Henderson, move to the left a little, right? So what can I pick up out of this? Well, let's say I wanted to compare Fullerton to Henderson. If I hold down my shift key and hit Henderson, now I can get what it looks like is happening between Fullerton and Henderson. I can look at both at the same time on this chart, which is kind of cool if you want to do some comparison work. The winds I can look at and I can go, well, if I'm at Fullerton at 20,000 feet, I've got 100 knot winds right now. So that's pretty strong. And you know, down to the surface, it's relatively calm here, right? And out towards the desert, we can see that the winds are actually a little bit less intense than they are over us right now as we go up in altitude until we hit about 24,000 feet, and then it's like way stronger winds. So if we were flying a private jet at 30,000 feet, we'd be dealing with some pretty significant winds. They'd be out of the northwest, so a little bit of a tailwind going on there. But I'm just going to go back and look at one of these charts at a time because we've got the winds, I've got the wind barbs, I know the direction the winds are coming from. That doesn't look like there's a super significant change in direction of the winds. This chart right here, here's what you can, this is the polar diagram of the winds over here in the corner. And if I start at the bottom, it's showing that the winds are out of the northwest. And as I go up in the chart, the little red dot moves. And look at, we saw a little change here, right? Winds shifted a little bit right here. And then it just continued to get stronger and stronger and stronger, pretty much in the same direction all the way up. And then there's some shifting going around as I get up in the altitude here. So this is what this is a polar wind chart. I don't really make a whole lot of use of that, but it's interesting. And then you can also see that if I move my cursor up and down here, I can get the temperature, right? So if I look right here, it's telling me that it's 35 degrees C right here. And how do I get, where do I get to zero? Let's go up, let's watch it climb. Right here, I get pretty close to zero. And that's about 9,000 feet. 9,500 feet is where the freezing temperature is. And my dew point is way over here. Plenty clear. I don't have any chance of clouds here. And what I'm missing, what's not on this chart right now, is my lifted parcel line. So how can I get that? Well, if I come over here and I place my cursor right at the surface where the temperature is and I click, boom, there's my lifted parcel line. And I can look at this line and go, no chance of convective activity tonight, right? No chance of that. And I have some strong winds to deal with. The higher up I get in altitude. If I had lifting going on, my lifting, let's see, we would have a lifted condensation level here at about 3,600 feet. So if there was lifting, if I had a cold front moving through, I would have to look at a surface analysis. I could have some clouds, but there's not much of a chance, depending on how much lifting is going on, of any kind of thunderstorm activity if I look at this chart. So this is an interactive one. The other thing that's cool about this chart is I could click, hopefully you can see my mouse, I could click over here and draw a box around this, and I literally can now zoom in and look at it up closer if I'd like. So the interactive chart, this is really one of my favorites to look at, is here. And I think Mike put that up on the screen for you if you want to take a look at that later. So I'm going to stop sharing this, and I'm going to go back to my presentation. All right, so those were, and then the other one I gave you previously was that university site. You can Google where to find these. They're all over the place. And if you might find some that you like working with more than others, but they're pretty interesting. All right, here's the 1-800-weather brief. This for those of you that used to look at these and don't anymore because all you use is ForeFlight or something nowadays. This took the place of Duets. Duets doesn't exist anymore. So if you go to 1-800-weatherbrief.com, you wind up with this menu. These are all graphical charts. They're beautiful. We're way better than the old days when we had to try and make sense out of where they were talking about weather being with these locations that maybe we weren't familiar with. This is all graphical now, which is wonderful. And down here at the bottom, under Other, is a Skew-T Log-P diagram. If you're interested, you can click there. Let's see. And that's it. I'm not going to go into ForeFlight use and any of this stuff, but I don't have any more for right now. I've been talking too long already. It's like hour 20. So I'm done, Mike. If you want to, if you got any questions, I'll do my best to answer them.
I think so far you've answered them all. I don't see anything coming through. Jeff did ask, why do we do Fahrenheit or feet for altitude and Celsius for metric value for temperature?
It's a really good question, and to tell you the truth, when I was in grade school, and I'm not going to tell you how old I am. When I was in grade school, they were going, any day now, it's all going to be metric. The United States is switching. We're all going to be metric, and it still isn't, right? So I don't know, except for the fact that a lot of the stuff we do is ICAO now, right? If you want to file a flight plan, you have to fill out the ICAO log. If you're looking at the temperature correction chart for landing at an airport that's, really, really, really cold, and you got to make altitude adjustments because you're in a colder air mass, it's an ICAO table, right? So a lot of our stuff is international, and I think we're slowly moving in that direction. And the mix is beyond me. We should all be talking millibars instead of feet, but we're not. And it's there's really it's a mystery. And I'm sure that
I've been flying to Asia and China a little bit lately, and they do their altitude in meters there. So we have right. our flight system on the airplane doesn't work in meters. We have to convert from meters to feet and put that in there. And it's just weird. Yeah, I agree. I imagine that you don't have a lot of questions because we put everybody to sleep. Well, they're hanging in there. The number of people online has been staying the same. The big question I'm getting here is about whether this presentation will be archived. And the answer to that is yes, we're recording it. And I'll make it available probably tomorrow, maybe Thursday. I'm not sure how to get the word out on where that's going to be. I'll post a link to it in the Fullerton Pilot Association Facebook page. That's probably the most universal one. So check in on that. Look at Fullerton Airport Pilot Association on Facebook, and it'll be there. Got a lot of comments about not ever having seen a Skew-T diagram before. Yeah, they're kind of, it's a rare bird. Well, they've been around forever, but they're not really covered a lot in aviation weather. You find it crops up, but for years, when I was teaching weather to students, I never covered it, but now I do. Now it's part of their weather brief when we go over weather, and I don't try to get them to understand the intricacies of it all, like I explained a lot of it tonight, but I want them to be able to get some useful data off of it. So, yeah, just for those of you outside, there was a newspaper article in Dallas posted on Sunday, and I saw that Sunday night. I sent it to Garry saying, hey, you might like this one. This is in a general newspaper article to the public, and it included a Skew-T chart. And I'm looking at the Skew-T chart, and based on what I learned from Garry's presentation just the other day, I'm looking at it going, wow, yeah, you can see where the freezing rain is happening. The temperature goes off and cools nicely, and then it warms up in this temperature inversion, and it gets above the freezing line for a couple thousand feet, and then it goes back down again. And that's a classic situation for a freezing rain condition. And you've been reading the news the last couple of days. You see what the weather's been like there in Texas, and you can see it all in that Skew-T chart. Yeah. Let's see, somebody asking about if they can get the slides only. Is that going to be available somewhere?
Just the recording. I don't normally send out the slides, but
Yeah.
I know that several folks, because they wanted to do review on their own, will look at the recording and do screen captures, and then they look at it that way.
Yeah, I do the same thing. I'm a little leery about putting the slides out and somebody trying to make a presentation based on it. It's my information. I have to talk around it, and so I get that. I agree.
Yeah.
Let's see. Yes. Denise asks, where on aviation.gov is that chart? And it's not on aviation.gov. I'll put this link again in the chat box here. There. So this is at RUC Soundings, RUC soundings.noaa.gov. And that was the page that Garry took us to a moment ago. You can type in the stations you're curious about. It'll show them. Torger's asking, do the airlines use these? No, we don't. We pretty much don't have any. We do use WSI, but they don't have SkewT charts available. We don't use them. So I'd really like to have that myself. Jason's asking, what was the university website? Do you have that back on your slide in the presentation again, Garry?
Hold on a second. Let me see if I can pull that up. So it's Plymouth State Weather Center. So you can Google that, and then it'll bring up the all of the menus at the top, and you click on Upper Air, and then CONUS for our little United States here, and then Soundings.
Yeah, Dan Llewell put a link down there in the chat box, so you should be able to click on that. Plymouth.edu, vortex.plymouth.edu.
Yeah, that's it.
Yeah, Dan's pretty resourceful. He'll dig up stuff like that. Good job, Dan. Thanks. All right. Well, the questions are dying down here a little bit. That was excellent, Garry. Thanks so much. Yeah, I'm going to have to go back and watch it myself. I was trying to figure out people's credits there. And again, if you want Wings credits for this, fling me an email at captainmikefast. Here, I'll put it in the chat box too. Here's my email for credits. Be sure to include the activity number. It's WP05103683. And I'm getting a lot of emails because the Orange County event is going on tonight too. So I'm getting a ton of emails from both of these events tonight. You might not get an answer. You probably won't get an answer. It's not because I don't like you. It's just because I got a million of them I got to go through. So let's see. And I don't see any other questions in there. If you want to take open season and let people unmute, if you're feeling lucky.
Well, I've got a couple more minutes, so yeah.
Yeah, until you say that's enough.
Administrative question. This is an encore reiteration of the encore from last week for SoCal Pilots, in which you covered the ForeFlight stuff. Has that been recorded?
Yeah, that was recorded, and it should be available on the SoCal Pilots website.
And this is sort of an extended subset presentation. That was a lot more, it started out with a lot more general weather. And tonight, Garry did just enough to give you the taste of what we're looking at in the chart. And then he expanded on that. So it was a portion of that plus a bunch about just SkewT. Let's see, hang on just a second here. Richard is asking a question here. I'll post the answer to this. I'll stick that in the chat box as well. So there's the WP number. If you send me an email, make sure to include this WP number in it. And I'll make sure you get credit for the correct presentation.
So why did I think this was a VFR into IMC seminar?
Yeah, you must have missed the first couple of minutes. The speaker I had booked to give us that presentation had to cancel Friday afternoon. So I replaced it with this one at the last second. There wasn't time to revise the FAA announcement for that. The speaker who I had scheduled for tonight is going to do it next month instead. That's the current plan. So.
Oh, great. I thought that was my usual crazy mistake.
No, it was me in the middle of this mess this time.
Oh no, that's cool. So I was late coming in because I didn't have that number, which Mike, thank you for getting it out there.
Yeah, we're going to fix that. For some reason tonight, the webinar was requiring the passcode to be entered separately. It shouldn't do that, and we'll endeavor to make sure that doesn't happen again, because I know that was very confusing for a lot of people and caused some problems.
I think that's in the settings when you set up the thing, if there's a box to check for that.
Yep, it is, and we just had it set wrong and didn't check it. So we will do that next time.
Super. It was very informative. For me, the SkewT thing has always been a mystery, and I've been to a number of classes about it, and I pick up, just a little bit each time, and fascinating stuff. I love it.
Yeah, I've seen a few things on it, and I think Gary's explanation of it is the best one I've seen. So I'm very happy to have him here to explain it.
Yeah, thank you, Gary.
Yeah, you're welcome.
All right. Well, I'm not seeing any more come up. But Jim, you have anything, any words of wisdom you want to close us out with?
You're muted.
He's got to unmute himself.
Okay, how's that? Any better?
Yep.
Okay, Gary, let me just take a moment to express my sincere thanks. I just thought that was an excellent presentation. Now, with that said, I'm going to have to go back and watch this about 3 more times to kind of get myself, my head in the game here. But I mean, I've heard about this SkewT, many times in the past, but it's starting to make a lot more sense now. And I can just see what a great tool that is. And so I don't know why we haven't learned this, years and years and years ago, but I'm glad to be part of it now. And I'm going to make an effort to learn more about it, because to plan a cross-country trip or even a local trip, I mean, what a great tool. So thank you so much for sharing your information with us.
You're welcome.
And one thing I'd like to add to that is to try to get a handle on how this works and how you can use it. I would suggest that any day when you happen to be outside and you look at what the clouds are doing, what the wind's doing, the precipitation, go pull up a SkewT for the Long Beach sounding or one of these local areas, and compare it and start building this database in your mind of what it looks like out the window versus what it looks like on the paper. And that'll allow you then to look at weather somewhere else, look at a chart somewhere else, and make a prediction or make a guess about what it looks like. And then go look at the regular METARs and TAFs and the surface analysis and so forth, and try to build that correlation. And you'll get better and better at it every time you do that.
Oh, I got another question. So you were showing the SkewT for Fullerton, but they don't necessarily have a sounding at Fullerton, isn't that right?
That's correct.
This is like interpolation.
Yes.
In between soundings, right?
That's right. That's correct.
Okay, cool.
So we did have a question pop up in the chat about were the soundings slowed or canceled during COVID, and I don't believe so. Weather reporting has to go on, and I've not been aware of any delays or cancellations in any soundings being taken.
So I agree with you. I think that the soundings went on. However, during COVID, there were times when some of the sites that put these results together weren't available to me. Like I would go there and it wouldn't work. And I'd be like, and it was a uniform, right? It was across the board. Like I have multiple sources for these things, and I would look at it and go, and none of them would come up with data. It was like, and so I actually wound up contacting one of the sources at one point, and he goes, yeah, we're having trouble accessing the database through the government sites that put this stuff together. So I think COVID did have an impact, but the weather balloons went on. So